Hi, this is an example problem on the photoelectric effect. Pause for a moment to read the question. All right, so we're given the work function of lead, the metal here, and we're asked in part A, determine the cutoff wavelength, i.e. the longest wavelength that will emit photoelectrons from lead. Well, to understand this problem, let's go ahead and look at the Einstein's theory of the photoelectric effect. Basically, this is an equation that is a conservation of energy equation. It says that maximum kinetic energy of electrons that are photoejected from the metal are related to the energy of the photon, and you subtract from that the work function of the metal. So let's go ahead and write that down. Ke max equals HF minus W0. So the work function is here in the metal, and the higher the frequency, the higher the energy. But remember that frequency and energy are related as well. C, the speed of light, is equal to the wavelength times the frequency. So if we solve for the wavelength, lambda is equal to C over F. So the higher the frequency, the lower the wavelength. Shorter wavelengths have more energetic photons, and we are looking for the longest wavelength, in other words, the shortest frequency that will eject an electron. Well, that means that HF, this term here, is just going to be barely enough to equal the work function. W0 is the energy it takes to knock an electron out of the metal. Think of it as like a potential energy the electron has in the metal. You have to give it enough energy for it to escape the metal. And the cutoff wavelength, as described here, this basically means Ke max equals 0. In other words, there is just enough energy in the photon for the electron to be booted from the metal, but there's nothing remaining to go into kinetic energy. It's going to come out of the metal, but just be at rest. If we do a little bit of math here, we can see that we can come up with an equation. It says H times F is equal to W0. And we want to use, we can calculate F now and then convert later to wavelength, or if we want, we can go ahead and substitute for our equation for F. So in this case, right, F is equal to C divided by lambda. So if we do that, we're going to go ahead and put in H. F is going to be C over lambda equals omega 0. Let's multiply by 1 over HC on both sides. We cancel these guys out here. And we've got the reciprocal relationship. So to calculate the wavelength, to solve for the wavelength, I need to take the reciprocal of the other side. Now, I can go ahead and, since W0, the work function is given in EV, I need to use Planck's constant, and there's two ways to write it, with EV or joules. I'm going to use EV because we're already given that value in the work function. So it's going to be 4.136 times 10 to the minus 15th electron volts times seconds, multiplied by the speed of light here, which is 3 times 10 to the 8th meters per second, divided by the work function for lead. It's equal to 4.14 electron volts. We can cancel some things out here, so the EV cancel, the seconds cancel. We're left with meters. Good. That's what the wavelength should be in. And when we put these numbers into the calculator, it comes out to about 300 times 10 to the minus 9th meters. Or we could say 300 nanometers. Now for part B, it asks, if instead we illuminate the lead with a wavelength of 125 nanometers, so shorter wavelength, right? Higher frequency, and since frequency is H times F, more energetic photon, right? So in this case, what is the maximum KE of the emitted photoelectrons? Well, we can go ahead and use the same equation as before. KE max equals the photon energy minus the work function. Let's substitute in again like we did before. For F, we're going to put in C over lambda minus W0. And in this case, we're going to put in Planck's constant again in EV. C divided by the wavelength. Now we got to convert this thing into meters, so 125 times 10 to the minus 9th meters, and then subtract from that the work function, 4.14 eV. Let's check the units here. Cancel our meters, cancel our seconds. We're left with EV, and that's right, since we're going to go ahead and subtract EV from that. Putting this into the calculator, we come up with a value of 5.79 electron volts. So that is the kinetic energy of the electron that is emitted there. Since the photon has a lot more energy than in part A, the photon is able to deliver all that energy to the electron. Part of that energy, 4.14 eV, is used to kick it out of the metal, but then there's still 5.79 eV left, which goes into the kinetic energy of the electron.